Swayam Prabha. Digital India. Educated India.
After understanding some of the terminologies and the issues that can happen while you do the switching and the routing, so now let's spend some time on understanding what are the different architectures or the design strategies available for designing the switches. So the packet switches in all, the fabric, when I say the switch here, it is the fabric, are broadly classified or of the two types. The first one is called the time division fabric, and the second one is called something called a space division fabric. In the time division fabric, what happens is only one pair of the port numbers are engaged in the conversation. So when I say that, if let's say 1 and 2 or input port number 1 and 2 are engaged in the conversation, so 3 and 4 cannot talk parallelly, only one pair at a time. So that kind of the strategy, if your switch fabric is allowing only the communication of that sort, then it is called as the time division type of the switch. And the second category of the switches are called as the space division switch fabrics, where multiple parallel connections are possible. So in this case, the same example, 1 and 2 can talk, 3 and 4 can talk. These are parallel forwardings that the switch fabric is doing. Though there is a connection between 1 and 2, there is a connection between 3 and 4. And each one of these, be it either the time division or the space division, they are again multiple strategies are followed. So among the time division, you have something called the seed medium and the seed memory. Among the space division, you have got something called a single path and the multipath. So we will take a look in detail of what is the seed medium and the seed memory, but let's understand what is the single path and the multipath. So single path kind of the switch fabric has got a unique path, a single path from one input port to the one output port. What I mean by that is, so let's say I have input port number numbered 1, 2, 3, 4 and output port number A, B, C, there are 4 of them. And there is only one and unique path to go to and reach from 1 to A. And there is exactly one path from how go from 1 to B. And the same thing applies for others as well. From 4 input to switch port number 4, there is only one way to go to A, there is only one way to go to B and C and D. So as many output ports are there, those many unique paths are there. And every time you have to forward a packet, you need to use only that path to do the establishing the connection between the input and the output port. But in the second category, where the multipaths are there, there are multiple paths available between an input port to an output port. So meaning maybe the simplest way is from the input port number 1 to reach the output port number A, you have two different paths, one this one and one through something else also you can reach. So like this, from every input port to every output port, there can be at least two number of the distinct paths that exist in your switch fabric. If your switch fabric is of that type, then it is called as the multipath switch fabric among the space division. Anyway, parallel connections are possible. When I say the parallel, these are independent parallel connections. So to the same output port number, two different people cannot anyway transmit. So that is not possible. But the independent transmissions like 1 and 2, 3 and 4, 5 and 6, they have nothing to do with each other's conversation. So they can engage in the transmission parallelly. So if your switch allows that, then that is called as the space division switch fabric. So let's go and see some of the examples of these switch types and try to understand little more detail how exactly they look like. So here is a picture. It is of the category called time division, where what we said, only one conversation from one input port to the one output port, it is transmitting the packet. And this is the time division is here implemented with something called the shade medium. So there is a shade medium. In the case there is a medium, here in this case it is a bus. So that bus connects the all the input ports and all the output ports. And as I said, bus is a shade medium. You can roughly compare this with the Ethernet technology, where only one sender and one transmit receiver is able to receive the only one sender is able to put the an Ethernet frame onto the link. Something similar is happening here. So if A is transmitting, none of these D, B and C will not be able to transmit it. If B is transmitting, no one else is able to transmit it. And transmission here means that B is simply putting the packet onto this bus, and there is something called as the address filter, and this is again exactly similar to that of the Ethernet. So when it broadcasts over the bus, the interface is going to select the packets or the frames addressed for itself, and then it will transmit it to the upper layer. So similar, the address filter here is on the broadcast medium on this bus, the packets are put. Now if it is meant for the port number A, and this address filter will take that packet and then put it into this queue. There is one queue corresponding to every output port, and similarly if the packet is meant for the second output port, maybe B, then there is a second address filter, and something like as many number of the output ports are there, those many queues are there, and those many address filters are there. And the address filter job here is to understand whether the packet is meant for the port number corresponding to itself. If it is meant, then it will pick up the packet and then place that in the queue. So that's all is happening. So again, only one input port can transmit the packet at a time. So although they may not be going to the same output port, even then it is everyone else is blocked when one is transmitting. That is the shade medium kind of the switch. It is a time division. So here you need to take turn. Once sometimes A transmits, sometimes B transmits, sometimes C transmit, and something like that. So that is what is the time division. So the other way to implement the time division kind of the switch fabric is something called as the shared memory switch fabric. So the conceptual idea here is you got a memory. In this case, here is the RAM, which is the central portion of the switch fabric, and there are two other components. One is called as the multiplexer, and the second one is called the demultiplexer. So demultiplexer is on the other side, and you can think of something like this. So the many inputs are coming and one output is going. This is the multiplexer, and the demultiplexer is the other way around. So you receive one input on one line and then you need to segregate it into multiple of them. So the shared memory here is the RAM. That is where the packets belonging to different output ports are placed in. So this can be very well a logical division, something like this. I have got a memory structure from let's say the starting address of this memory is 0. From 0 to 100 bytes, this is the key where the queue corresponding to the port number 1, or maybe that port number is A. So the Q1 is logical entity within this address space, and from the address number 101 to somewhere around 200, this is the Q2 corresponding to another port, output port number B, something like this. So whatever the queues are there for each of the output port, they are actually organized into the same memory. So if something is not occupying, probably you can vary the amount of the space given to the other queue and then logically adjust where exactly the Q1 starts and ends, where exactly Q2 starts and ends, something like that you can do. So the point is, there are two components, one is the multiplexer and another one is the demultiplexer. They are sitting at the two end points of the switch fabric, and inside this the link whatever is shown here, here is the memory where the packets are actually getting received and then they are placed there inside that memory station. So you can very well schedule what is shown here as the with the arrow marks from the this is the color coding of the packet received on this particular port, maybe the port number 1. This is the coding of the packets received on the port number 2, and this is the color coding of the packets received on the port number n. When you say the it is the input port number, and then you identify where exactly they need to go, and then accordingly you can schedule them, taking the enemy packets are placed in that queue, and then you can mark them and send it to the appropriate output port. So again, as only memory is one, so you can read the data from only one location at a time. So this is a single operation. So when I am when I am transmitting the data corresponding to packet of let's say this is P1, and I cannot really do or fetch the contents from the packet, another packet to go, supposed to go to some other port number. So only one operation is happening at this point of time, only one read and one transmission. So that is why this is a time division operation. So this is implemented with the shared memory. So these are the two things, one shared memory and the other one is the shared medium based implementation. Both of them are in either of these two cases, the transmission is taking turn. One packet from one input port is getting transmitted onto the output port. And the second category, as we saw, is the space division, where parallel transmissions are possible, and we understood that there are again two variants of the space division technique. One is the single path and the multiple path. So single path from the ith input port to the jth output port, there is a single path exists. Here is an example of that kind of the switch design called as the crossbar switch. The name of the switch technique, the fabric crossbar, comes from the two different states in which these elements, these are called connection elements, can be. So one in a case it can be in the cross state. So this is the cross state, and the other one can be in the bar state. So these are the 4 points, and on 4 sides you have a link, and it can connect to 2 of them, something like this. So this state, if the connection point is in this state, then it is called as the bar state. So all these connecting elements can be either in the cross state or in the bar state. So that is where the combination of these two states is called a crossbar switch. And the way the crossbar switch is organized is the switch fabric corresponding to the crossbar design is something like this. So on the left hand side, what you see is a bunch of input ports, and what is shown at the bottom here is the output ports. Here in this case, there are 4 input ports and the 4 output ports, and so the depending upon the number of the input ports and output ports, the number of the such crossbar points that are there inside this design is n cross n. So if you have n number of the input ports and m number of the output ports, you will have n cross m number of the such interconnections. So one of the issue with this kind of the design is, see, the number of the interconnection points that you require inside the switch fabric will grow quadratically, meaning, so here in this case you have 4 input ports and 4 output ports, you require 16 number of the such interconnection points inside the switch fabric, and if you increase the number of the input and output ports, maybe instead of 4 you make it 5 and 5, then you require 25 number of such interconnection points. And one of the advantage of such a crossbar switch is there is no internal blocking that is happening here. So for example, if 1 and 4 wants to engage in the conversation, So all that I need to make is make this connection established from this link, this link, this link, and then come to this link and connect this. And vertically also you need to connect them. So this will not block any other conversation not involving port number 1 and 4. Meaning if I want to engage in the conversation of 2 and 3, I can still do that. How do I do that? You establish this link, this link, this link, and then this and this vertically. So you come to the port number 3, 2 and 3 can also talk. Similarly, 3 and 2 and can also talk, 4 and 1 can also talk. And it might also happen that 1 can talk to 1 can send 2 can send it to 4, 3 can send it to 3, something like that. So as long as the input and output pairs are different, so you can still establish a unique connection between the input port to the output port and transmit the packet. So this is, there is only unique path between one pair of the input and output point. So when I want to transmit from port number input port number 1 to the 4, this is the only link that is available. So that is the link I should take. And if I want to transmit to 2 and 3, this is the path that I should take. So nothing else. That is how it has been designed. So like this, there is a unique path between every pair of the port numbers, but it is not internally blocking the other parallel communication. As long as the input and output port numbers are distinct, you can still establish the parallel connections. Parallel transmissions are possible. As I said, a single disadvantage of the such a switch is basically the number of the interconnection points are increasing as the number of the ports are increasing on the switch. So it internally it means that the size of the switching equipment fabric itself will grow as the number of the interconnection points increase. So you need to package those many number of the interconnection points inside your fabric. So size will grow, and that will have other implications. So as the size grows, your overall switch size or the router size will increase. It requires larger space, cooling equipment, and other things come into picture. So that is one major disadvantage why this crossbar switch is actually not used in practice. And the other second kind of the space division kind of switch, again with the single path, is something called as the fully interconnected switch. So the fully interconnected switch, the way to understand it is there is a link between every input port to the every output port, and that link is a direct link. There is no intermediate stages that are involved, unlike the previous case where when you want to go to from port number 1 to port number 4, you are crossing multiple interconnection points. Those are not there. And one of the simplest way to implement this kind of the fully interconnected switch is to maybe have a bus which is actually connecting each of the input to port number to each of the output port number. So that bus, when that bus is dedicated to that particular input port, but it is connecting to all of the output ports. So when a input port number 1 wants to transmit, it can do an independent decision of transmitting, and the probably what can happen is the packets or transmissions from the input port number 1, 2 or some other port number can collide at the output port, and then thereby you bring the issue of output blocking. That might happen, but as long as the paths that exist, the number of the links that exist between the input port and output port are unique. So that's why this interconnected switch is actually falls under the category of single path. There is a unique path, and but the switches, the input and output ports are actually directly connected with each other, and that's the example. The other way looking at these, in order to bring the scalability to the switch design or the fabric, number of the elements of the interconnection points that you want to place in the switch fabric, people found out different techniques to enhance. How do I modularly build the, for example, if I take a component or the switch fabric design for connecting two different port numbers, 2 cross 2 in 2 input ports and 2 output ports, and then using that as a building block, can I extend modularly and come up with higher order designs? So using the 2x2 switch component switch fabric design as a building block, can I build a 4x4 switch fabric, or can I build an 8x8 switch fabric? So that is precisely what is done here. So this kind of the design, what is shown on the right hand side here, is something called as the banyan switch. So this is an example of a 4x4 switch design with 2x2 switch stages. So here this is still a single path switch, where the path that exists from one input port to the one output port is still unique. So for example, if I want to go from the input port number 1 to the A to A, so this is the only path that exists in this particular design. So there is no other way you can reach the from input A to another output A. So for example, if you take this path particularly from this one, and then you can go to the one, then you will not be able to reach A. So there exists a unique path, but this is modularly designed using the 2x2 switch fabric as a building block. So this you can think of as a way of extending the switches, the design to the higher order. So, but there are other designs available as well. So you can make it multi-path using the same designs technique, using the 2x2 switch fabric design as a building block. You can also construct the multi-path switches as well. So we will take a look at one of those examples in the subsequent slides. So this banyan switch, as I was talking, is a single path and switch. There are multiple ways of designing, that's what I said. So here what you see on this slide are the three different variants of the single path banyan switches. In fact, these turns out to be isomorphic to each other. So what mean is, the structurally they are similar, but only the way they look like, the organization, the links, they are actually looking slightly different. So those designs are called as delta, omega and banyan. So these are broadly falling under the category of the banyan switches, but they are structurally isomorphic to each other. If you think this as a graph with the interconnecting points as the nodes and the links between them as the edges, then these are structurally isomorphic to each other. They are exactly same. Isomorphism means that they are exactly structurally they are same, but the way they look like might be different, but they are exactly the same graph structures. So this is an example. Again, although the connections look little bit haphazard, but you can think of there is only a unique path that exists between the one port to the another port. For example, if I want to go from the input port number 1 to output port number A, this is the only link that exists. So if I take any other path, then I will not be able to reach it. So similarly, if I want to go from, maybe I'll number these as 1, 2, 3, 4, 5 and 6, 7, 8. There are 8 input ports, the output port A, B, C, D, E, F, G and H. So if I want to, let's say I want to go from the input port number 6 to F, how do I go that? Maybe I should take this link, go here and then go here, here and then go here and then go here. So this is the only path that exists. If you take any other path, then you will not be able to reach to the output port number F. So that's what it is, single path between any input port to the output port. So same argument holds good for the other combinations as well in this all the three variants. So that is the single path where any two pairs of the input and output ports have got the unique paths. Now let's take a look at the multi-path switches, where the from the one any input port to the one output port, there are multiple paths available. So the simple way to look at it is, so on the input port 1 and the output port 1, so one link is this one, and the second link is I may not be going directly to this one, I go to an intermediate connection point here, from here to this link is possible. If you have such a design, then it is called as the multiple multi-path switches. So here is an example which is a variant of the Bunyan switch called as the augmented Bunyan switch. So here there are multiple paths available from the input and output pairs. So for example, if this is the input port number 1 and this is the output port number A, and one path from the A1 to A is this direct link which is running in the straight line fashion. And the other way to possibly go there is to maybe I can go from here to here, and yeah, this link and then this link, this link, this link, and then go here and connect. Okay. So this is the connection between the input port number 1 and the output port number A. So there is two distinct paths, one in the straight line fashion, the other one that I just drew. So these two distinct paths are exist. So by virtue of that, this is a multi-path design. The similar argument actually holds good for the other input and output port pairs as well. So there are indeed multiple paths from every input port to the every output port. So such a design is called as the multi-path design. That is one example. The other example is something called as a multi-plane switch, where there is not one. The way to understand the multi-plane switch is to again there are some input ports and output ports, and there are multiple switch fabrics sitting in between, which are actually operating independently. So what is shown in this diagram is there are three planes, plane number 1, 2 and 3. So you can very well think of them as replicated versions of the switch fabric. I can very well come up with whatever design I want to do for the designing the switch fabric number 1, 2 and 3. So let's say I go with the crossbar, and there is one plane with one crossbar, there is a second plane with a second crossbar, something like this. By virtue of replicating them, I bring the parallelism in the transmission. So the some input port can to some other port, and I can do the parallel transmission. So from I and J, A and B, something like that, parallelly they can transmit it. And again, since these every plane is connected to the every input port and every output port, there is an inherent multiple path that exists in the transmission. So one plane is connecting to every input and output port, even though it might be transmitting only doing one time, can connect to one of the input and output port, because there are multiple such planes available. So you can think of, because the second plane is also connected to the same input port and the output port, you can bring the parallelism in the transmission. So that is an example of the again multi-path switch. So often what can happen is if you can recollect our earlier discussion, there is a processor which is actually is in the control unit, which actually establishes a link between the input and output port. And we understood that there are two categories of them. One is the centralized processor, and the second one is the distributed. The distributed processing mechanism is often also called as the self routing, and what it means is the decision of transmission can be done independently on each of the port. So when a packet is available at the input port number 1, that control unit can take the decision for forwarding or establishing a link, and on the second input port, maybe on port number 2, there is a second component sitting that can also independently decide. And once we lose the central control, because the forwarding decisions or establishing the links between the input and output ports are distributedly done, so the two of them can parallelly decide at the same time instant t, they can decide I can transmit it to port number 3. So for example, one also wants to establish a link to port number 3, and 2 also wants to establish a link to port number 3, and here is your port number 3. Then because these decisions are not centrally coordinated, they are independent, what might happen is you end up with what we discussed as the output blocking. To both of them want to go or access to the same output port. Now, if two different transmissions from two different ports by virtue of two independent decisions start arriving at the output port number 3, you will have an issue. You need to arbitrate them, and then need to ask someone to take it back. So, this is a switch design which is called as the recirculation mechanism, where by virtue of the arbitration you are able to decide one of them, you are going to pick up one of them. So, either one is going to transmit or two is going to transmit, and whatever you are not transmitting at this point of time, the bits corresponding to that packet need to be put it back to the same queue from where it came. So, that is what is done here. So, if because of the output blocking and independent decision, or the distributed transmission decision, distributed transmission processing happening in the switch fabric, two different transmissions ending up at the same output port, and what because of that you have the output blocking, and then you are taking back one of the packets or the transmissions corresponding to one of the packet back and putting back into the same queue from where it came from. So, such a design is called as recirculation. So, here you have the multiple paths available between one pair input port to the output port. Parallel transmissions are possible, but those parallel transmissions are not like this. As long as they are independent, then you can do the transmission. So, again, there is from the one input port to the one output port, there are multiple transmissions, but only one path you can take at a single point of time and then do the transmission. So, you cannot really use the parallel paths that exist for transmission from the same input port number 1 to the same output port number A, and assuming there are two different paths exist, it does not necessarily mean that I will be able to transmit two different packets from the same input port to the same output port. From 1 to A, there are two different packets are not parallelly transmitted. Only one packet is transmitted. You take either the path 1 or path 2. By virtue of that, you are making use of only one of the existing paths in the switch fabric. But in a way, you can understand this as the alternative things are given to you. When you are not able to make use of the other path, then you go via alternative route, so that you maximize the number of the parallel independent transmissions in the switch fabric. So, that is the recirculation switch, which is of the type multipath switch type. So, let us spend some few minutes in understanding the something called as the buffering strategy. What we said is the end user traffic is bursty in nature, or any transmission in the network is bursty in nature. So, bursty in nature means you will have a surge of the transmissions at a shorter period of span of time, and then there might be something where you may not be having enough transmission. When you have got bursty transmission, so, the transmission rate, the rate at which the switch fabric can actually transmit from one port to the another port, or some input ports to the output ports, is limited, and even the input lines have also got, or output lines have got the finite capacity with which they can do the transmission. And if there is bursty transmission, then probably you require a mechanism to hold those packets inside the switch. So, that is what where the buffering comes into picture. This is fundamentally to handle the bursty traffic in the network. So, now what this buffering strategy briefly about is, where exactly I am going to place this buffer, where exactly I am going to hold these packets. So, one mechanism that we earlier touched upon is something called as the logical queues, where you got a single memory that could very well be a RAM, and then you earmark, this is the portion buffer for the port number 1, this is the portion from 0 to address number 0 to 100, this is the queue for the port number 1, from 101 to 200 you have the second queue, and from 201 to 300 third queue, something like this. So the memory is one, but you logically divide that memory, and then you put when the packet comes on input port, so you decide on which output port it is supposed to exit, and then pick up that packet and put it into the queue or the memory portion corresponding to that output queue. This is one way of organizing or storing the packets inside your switch. And the second strategy of placing the queues is, you might have very well have n different buffers available at each of the output port, and packets are coming on the input port, and then you switch fabric is establishing a connection, and then you come back and put them in the respective output ports. So, n independent memory, n independent queues, and each queue corresponding to one of the output port, then you you schedule the packets for transmission from that output queue and then do the transmission. And here there is no buffering that is happening at the input queue. So, the packet will be you will be able to transmit that packet only when you are able to establish a connection from the input port to the output port right here. Otherwise, the transmission, the packet will be lost. The third strategy of the buffering is, instead of doing the buffering at the output port, you do the buffering at the input port. As and when the packets arrive, you put them inside the buffer, that is the input buffer. So, there are as many buffers, as many queues as there are port numbers. So, there is one queue for the input port number 1, and there is one queue for the input port number 2, 3 and 4, something like this. And you put the packets there, and then you look at when the switch fabric is able to establish a connection for your transmission, that time you pick up the packet from that queue and do the transmission. Fourth way of looking at the buffering is, or the way it is done is, place the buffers in both the places. You do have a queue at the input port, and also you have a queue at the output port. And in fact, most of the examples that we saw in the previous discussion, in the previous lectures, we did say that there is a buffer, input buffer, and then there is an output buffer. So, here is an example of that. So, there are n different input memories, n different output memories, and then the packets are coming, you place them inside the input queue, then do the FIB consultation, establish the connection through the switch fabric, place them in the output queue, and then you can do the scheduling operation. So, scheduling is done both at the input and the output queues as well. So, this is the fourth strategy. So, all of these can very well handle the bursty transmissions that usually happen in the network. So, with that I will stop it here. Thank you.